Welcome to lesson 34. So we're going to continue talking about single proportions, which is a categorical variable. This time we're going to look at performing a hypothesis test. So this is when you might want to test, hey, is the proportion of OSU students that has student loans, is that higher than 0.25? You might want to test that, or a number of other things. Okay, so when do we want to use a z-test here? Specifically when we want to calculate the proportion value P for just one population. There are z-methods for testing the difference between two populations. If you continue on to ST202, that will be something you do. We aren't going to do it here in 201. So as always, we're going to want to use the condition that we have taken a representative sample. The easiest way to do this is to take a random sample. And then here, so note this is a tiny bit different. The sample size being big enough now has P naughts in here, not P hats. So it's not necessarily how many successes and how many failures you observed. What it is if the null is actually true and the proportion is equal to whatever value you're testing, would your sample have been big enough that you would have expected to see at least 10 in each category? So it is a little bit different. And then setting up, though, the hypotheses, they're going to be very, very similar. You can have less than, you can have greater than, not equal to. And we're going to be calculating a z-test statistic. So the top, it's going to be what you observed in your sample, P hat, minus P naught, so minus what's claimed. So what you actually observed minus what's claimed. And then on the bottom, this standard error value on the bottom has P naughts in it. So the part under the square root does not have hats, not for a hypothesis test, because a hypothesis test assumes that the null is true and that the value for P is P naught. Confidence intervals, in their own way, they assume they don't want to know about any claimed value. They only run off of sample information. So definitely keep a note that the part under the square root for a hypothesis test will have P naught, the claimed value. So suppose, because I am very stuck on if people prefer whether that's too cold or whether that's too warm, I was reading through and I found an online poll that claims 55% of Americans say they would prefer whether that's too cold over whether that's too hot. So we want to know, is there evidence that OSU students' opinions are different than this claim? And we have a significance level here of 0.10. So just to reiterate here, we had 145 folks prefer whether that's too cold out of 191 folks total in our sample. So what is my question of interest? So for any sort of hypothesis test, it's going to be a yes or no type question. So is this, and then we're looking at different from. So is the proportion of all OSU students that prefer whether that is too cold different than 0.55 or 55%? So once again, if I have this set up just right, I could say the proportion of all OSU students that prefer weather that's too cold. That's my parameter of interest right there. And is a yes or no question. So my parameter of interest, it's what I just said there, that proportion, and it gets that notation, just the letter P. And you might think, well, why is this not a Greek letter? We used to use the Greek letter pi, but we also used the Greek letter pi to represent other things, so it got really confusing, so we decided to use the letter P. Trust me, it's a lot less confusing, at least for us. So inventory, this should look very, very similar. So X, that's my number of successes. It's just that 145. My P hat is that 145 over 191. And my sample size is 191. And we do have an extra piece here. We need to have that claimed proportion. So I'm just going to use this 55. So remember, this value should never come from the sample. It should never come from what we observed. In theory, we're supposed to have it before we even collect a sample. So P0 should never come from any sample information ever. So that 0.55. So moving on down my steps, what's my significance level? That is just this right here. So typically we will give you a significance level. Anytime we don't, you can assume by default it's 0.05. However, if we give you one, use the one we give you. So checking my conditions, so that did I take a random and representative sample? This is the same as before. No. So we're going to write an asterisk saying, hey, this may not apply to all OSU students, because absolutely I took a convenient sample. I had a bunch of ST201 students right there, and I went ahead and I asked everybody in that group. So this is slightly different than before. Conditions-wise, I need to know, is a sample size of 191 big enough? I can tell you right off the bat, probably, but let's check. So if the null is true, and I took 191 folks, and I could expect 55 of them to prefer too cold, then that means on average, so if I were to repeatedly take samples of 191, I could expect about 105.05 on average to indicate that they prefer too cold weather, if the null is true. So this is at least 10. That's good. And I can tell you right off the bat, if this number, well, here, let me show you first. So then if I want to do 191 times 1 minus 0.55, I'm going to get 85.95. And this is greater than or equal to 10, right? 85 is higher than 10. So things to note, if you add these two numbers together, you're going to get 191. So right off the bat, what I typically do, if P0 is smaller than 0.5, then I go ahead and I really focus on this. If this is at least 10, you're going to be good. But if P0 is bigger than 0.5, this means that 1 minus P0 is smaller. So if that comes out to at least 10, you're going to be good. For me even, I calculate the first one to be 105.05. If I know that I have to add more than 10 to get to 191, I'm going to be okay as well. So just know that there's some just real quick ways to just see it, whether or not you have that size requirement. So stating the hypotheses. So I'm going to have my null, and I'm going to have my alternative. So things to note, I am dealing with proportions and not means. So that means I should have P. So just focusing on the null hypothesis, remember I should always have an equal sign. And then this should be the claimed value. It should never come from the sample. In fact, nothing to do with our hypothesis should ever have anything to do with our sample. We're going to pretend that the sample is collected afterwards. So this should be what, 0.55. So I'm going to have 0.55 here as well. And then this comes down to the question of interest. So we just wanted to see if OSU opinions are different from. So we don't have a particular suspicion that they're higher or lower. So not equal to. And so this is going to be a two-sided test. That means that when I calculate my Z statistic and get a one-sided p-value, I'm going to multiply that one-sided p-value by 2. And I'm going to have a two-sided p-value. So now I'm ready to go ahead and calculate my z-test statistic. So here I get, so what I observed, so 0.759 minus what's claimed, 0.55. So right off the top, I know that my z-test statistic is going to be positive because what we observed in the sample was higher than the claim. And then sticking in here, so 0.55, when minus that, it's 0.45 over 191, square root all of that bottom there. Okay, so for the top, I'm going to get something like 0.189 over like something small, 0.036. I didn't round here when I made my calculations, but just to let you know roughly what you should be getting on the top and the bottom. And so I ended up getting a z statistic of 5.28. And I hope this sets off an alarm bell in your head, because that's a really big z-test statistic. In general, any test statistic that's, further out than like 3 or so, it's pretty big. So that means it's really far, so 5.28 standard deviations from above the mean. This means it was a lot higher than the average. So I want the probability, technically I want the probability that it's higher than this positive 5.28. Because I want the area above. Because if the null is true, and it's 0.55, and I saw 0.759, as or more extreme is going to be higher than. So I want the higher than area. So I'm going to look for, I would need to break it into 5.2 and 0.08. But before I really go into that, let's look. So I have the entire z-table, the positive z-table split here. So I go from 0.5 to 1.9. I go from 2 to 3.4. And then that's it here, right? It doesn't go higher. So the probability that z is higher than 3.49, because this is the highest it gets here, right? It's going to be 1 minus that 0.998 equals 0.0002. I want something that's even higher than 3.49. So if this is 3.49, 5.28 is even further out, which means this area is smaller than this. So my one-sided p-value is smaller than 0.0002. If I want my two-sided, I would just multiply everything by 2. So my two-sided p-value is smaller than 0.0004. Which I hope we can agree that's pretty small. That's 0.04 of 1%. It's really small. Like 0.04%. So throwing this actually into a calculator, I got something like my p-value, which is very small, is equal to like 1.288, I'm rounding here, times 10 to the negative 7. That scientific notation, if that's not great, that is like saying 0 and then 6 zeros here after the decimal. So 1, 2, 3, 4, 5, 6, 1, 2, 8, 8. This is really tiny. It's totally okay to just say p-value less than that small number. So telling me that it's less than 0.004, that's good enough for me. So less than 0.0004. Although if you use the calculator, you can put that if you want, although that's really, really small. I wouldn't want to write that many zeros at the 0.10 significance level. So things to note, I have a really tiny p-value, and it's definitely tinier than that significance level. So I should reject. So we reject the null hypothesis with a p-value of less than 0.0004 at the 0.10 significance level, which is very statsy-like, right? So if you tell your grandmother, she'll nod her head and go, that's nice, dear. And then here's the sentence, that translation sentence. So we have very strong or convincing evidence here, because that p-value is tiny, to suggest that. So now I need to say the alternative hypothesis, but in context. So the proportion of, now I name my population, so all OSU students that prefer too cold weather is different from, oops, that's a goofy looking R, and then that 0.55. So we have really strong evidence here that the proportion of all OSU students that prefer too cold weather over the too hot is different than 0.55. So it's definitely different than this article claim. And then it's probably still worth noting, like, may not apply to all OSU students. Right? Because I took a convenience sample, and I really ought to be wary of that. It comes down to my sample of ST201 students. Who does that really represent? Does it represent all OSU, or does it pretty much represent just itself? However, the write-up should still be about the population. Okay, so I wanted to throw this out here because there's definitely a lot of p's involved, right? Like, we have p-value, and I didn't throw that in there. We have p-naught, we have p-hat, and we have p-star. Ugh. So p-naught, you're going to use in hypothesis tests only. P-naught's not going to be used anywhere else. So p-naught is a claimed value for the proportion, and it does not come from the sample. And we do use p-hat in here, but we only use it in that numerator. So what you observed minus what's claimed. And then everything under the square root, it's p-naughts and not hats. Then, when we go to confidence intervals, it's only p-hats. You're not using anything else in your confidence interval. Your confidence interval can be based completely on what you saw in a sample. It's never based on what's claimed. And then p-star, so that comes in when you want to calculate a sample size. So you're saying, hey, I want a 95% confidence interval that's no wider than 0.10 or however long. You have your margin of error, and then your p-stars. So if you know nothing, there's no pilot study, there's no sample that you've collected already. For p-star, you need to plug in 0.5. But if you do have sample information, use p-hat. So that's where p-star comes in. P-star is specific to calculating the sample size. P-naught is specific to hypothesis tests. And then confidence intervals only has p-hat. So we have a couple more examples. This is a chocolate example, and I want to say we have one more calculating the sample size after that. So looking here, we have a factory that they want to know, would purchasing robots to assemble boxes of chocolate be feasible. So what they're saying is they're on an assembly line and they want to know if this robotic arm, packing this box of chocolates is reasonable. They don't want to have defective boxes, and they want to be, fairly efficient. So they go ahead and they get a set of robotic arms and they have them assemble some chocolate boxes. So after a period of time, they go ahead and they randomly select 500 of the boxes that this robot pair of arms has put together. And out of those 500, 17 were defective, which is like, oh no, somebody's going to have to eat it now, right? So they want to know, what the defect rate of this robot arm is. So we're going to calculate a 95% confidence interval to estimate the true proportion of defective boxes when the robot is used. So remember here, looking at a 95% confidence interval, this tells me that the question I ask should be open-ended. So like, what is? So what proportion of all chocolate boxes arranged by the robot are defective? That's what we're going to start. You could have said, what is the proportion of all boxes that are arranged that are defective? Either is totally acceptable. So remember, if we have this set up right, proportion of all boxes arranged by the robot that are defective. It is quite a wordy sentence there, but that's what we're looking for. So my parameter of interest is going to be P, because I want it for the population. So I want to make a statement about all the boxes that this particular robot arms makes. So the proportion of all chocolate boxes arranged by the robot that are defective. And then inventory. So I have a sample size of 500. That's quite a bit. It's a big sample size. I have 17 observations that were defective. I'd like to point out, this is why I do air quotes successes, because here our successes are defective boxes, and most people would not consider that a good thing. And then P hat is going to be that 17 over 500. It's going to be really small, something like 0.034. So it looks like 3.4% of this sample of 500 boxes that the robot put together, 3.4% of them were defective. So, they can just send them over to me. I can test the chocolate. It'll be fine. So my confidence level, that's just right here. By default, if we don't give you a confidence level, you can assume 95%. It's kind of like with hypothesis test. You can assume 0.05 significance level if we don't specify one. And since that's a 95% confidence interval and we're using Z methods, I can use a Z star critical value. And that's just going to be 1.96. So then checking my conditions, did we take a random sample? Yes. So 500 boxes are randomly sampled. Yes. So yay. We can say that these 500 boxes represent the boxes, like all the boxes that this robot arm makes. At least in this productivity period. And then based on the central limit theorem, so is our sample size big enough? So we had 17 defective ones, which means we had 500 minus 17, so 483 not defective ones. So if you wanted to do the math, 500 times our p hat was 0.034. That's just going to take us right back to 17 defective ones. And that is at least 10. And then this one is saying, okay, well, how many not defective ones? And 483, that's a lot more than 10 as well. But if you want to plug it in, 1 minus 0.034 is 0.966. And you would get 483. And that's higher than 10. So you're good. So we're ready to kind of start plugging everything in and calculate our confidence interval. 500 is such a nice big size there. So I have everything I need after I have these three values to plug in here. So what I observed in the sample, 0.034, plus or minus, so 1.96 times the square root of, so 0.034, 1 minus that, so that's that 0.966, all over my sample size, which is 500, square root over all of that. And I'm going to round just a little bit here, because I think this right here, that ends up being like 0.0159 after you round a little bit. End up getting 0.0181 to 0.0499. And remember, there aren't units, so I don't need to add those. Also, note, this is kind of close to 0, right? 0.0181, that's 1.81%. It's pretty small. If this lower bound went into negative values, and you think about it like, oh, the proportion doesn't make sense to have negative values, you would cut it off at 0. Just like if this upper one went above 1, and that proportion doesn't make sense to be above 1, you'd cut it off at 1. So just note there are times that it makes sense to cap off your confidence interval in one direction or the other. Sometimes both. Hopefully not, though. If you're going below the minimum and above that's pretty much the entire interval that you could, it's a 100% confidence interval. So just to write that back out again, 181 to 0.0499. So we did a 95% confidence interval for the proportion of, and here's my population, so the proportion of all chocolate boxes, arranged by, sorry I'm running out of room, robot arms. Technically in this productivity period, although, I mean, you're welcome to be that specific if you want. That what? So the proportion of all those boxes that are defective. Is estimated to be between, and here's where this comes in, and remember, no units, so 0.0181 and 0.0499. Remember, you should always say from the smaller number to the bigger number. We're real sticklers for that one. With a point estimate of, so this is that, p hat. So 0.034. And if you double check, 0.034 should be exactly in the middle here. If you averaged the two ends, you should get 0.034. So looks like on average here, this robot arms, when they're arranging chocolate boxes, somewhere from 0.0181 to 0.0499 of them are going to be defective, it looks like. So same problem, but now we're going to shift our question and our focus here. So they want to know if it's feasible, so they go ahead and they said currently, and this is where it starts being different right here, currently this work is done by human assemblers. And the human assemblers we know have a defect rate of 3.6%. We want to know, is there evidence that the robots have a different proportion of boxes that are defective than the human workers? And so it gives us a significance level 2. That's great. So right here, this is the sentence that really captures largely what we're looking at. We will want to have the 3.6 number in there though, because that's the claimed value. So my question of interest should be yes or no type question. Is the proportion of all chocolate boxes arranged by the robot that are defective different than the human rate of 0.036? So it's really important that I include this number. The human rate bit, that gives me a little more information, but the really mandatory part is this number here. So, and it's different than, because they just want to know if it's different. Although, quite honestly, it would be reasonable if they wanted to see if it was lower than, right? Because ideally, if you are looking to replace human assemblers with a robot assembler, you're going to want it to make fewer defective boxes on average. So, but here we're looking at different. So here, my parameter of interest, it hasn't changed. It hasn't changed since we were looking at the confidence interval. So it's still that proportion of all the boxes made by this robot or assembled by this robot that are defective. And the notation is still going to be P. So inventory, so it's going to be much the same. So I have 17 defective ones. I have 500 in the sample. P hat, so what I saw is 17 out of 500 are defective. That's 0.034. And then P naught. So that's that 3.6%. So I'm going to convert it over to proportion. So 0.036. And just looking real quick, I mean, 500 is a big sample size though. 3.4% doesn't strike me personally as very different from 3.6%. So we're going to see, do we have enough evidence to indicate that it's not the same? So my significance level, I'm going to just pull it straight from here. So then looking at the conditions, the first condition should be the same as it was in the confidence interval. We want to know, was the sample randomly selected? Can we say within reason that it represents the population, that these 500 boxes reasonably represent all of the chocolate boxes this robot arms are making. Then what changes though is, assuming the null is true and robots really have the same defect rate of 3.6%, did we take a big enough sample size that we could have expected at least 10 defective and at least 10 not defective? So was our sample size of 500 big enough? Chances are yes, 500 is pretty big, but it's worth checking. And I mean, definitely there are times when P naught is really tiny, like certain diseases and whatnot that have really, really just low prevalence. You're going to want to make sure you take a big enough sample size to see at least 10 individuals with it. So 500 times, now we're looking at 0.036. This is going to come out to 18. So if the null is true and really 3.6% of the robot's boxes are defective and we took 500 boxes, we'd expect around 18 on average to be defective. And this is at least 10, so that's good. And then conversely there, if we expect about 18 on average to be defective, that means we expect like 500 minus 18 or 482. So 0.963. No, I can add sometimes. That should be 482. And that's at least 10. So things to note, that If you expect 18 defective, you expect a lot more than 10 not defective if there's 500 of them. So yes, I would say we definitely have a big enough sample size that we could assume this. So state my hypotheses. I'm just going to write them out here. So H0 and HA. So just getting started, I am looking at whether something's defective or not. So that's categorical. So I should have P. Never a hat. There should never be a hat ever in hypotheses. We will flip out every time. So P. And remember, there should be an equal sign in the null. And then claimed. So remember this value, it should be what's claimed or what you're interested in comparing. It should never come from the sample. So 0.036. And then 0.036. And the sign that goes here depends on our question of interest. So we want to know if that proportion is different than. So we're going to use a not equals sign. But things to note, this is a two-sided test. So that means when we find our one-sided p-value, we're going to multiply by 2. So just filling out here, 0.034 of our 500 boxes were defective. So that's our sample. 0.036 is the claim. So I have everything I need to plug in. Remember, on the bottom, it needs to be the claimed value under the square root. So the top, what I saw, so 0.034 minus what's claimed, 0.036. So right off the bat, I know that my z-statistic is going to be negative because what I saw in my sample was lower than what's claimed. So then, 0.036 times 1 minus 0.036 is something like 0.964 over 500. That 500 is going to make this standard error on the bottom pretty small. I'm going to get something like negative 0.24. So just things to note as far as standard deviations away from the mean. This means that what we saw in our sample is 0.24, so not even a quarter of one standard deviation less than the mean. So it's pretty close to the mean. I think it's very likely with something that's so close to 0 that we're probably not going to have enough evidence to say that what the robot's doing is so different from the humans. So looking here, negative, so if the null is true, I like to do this, it's really 0.036. What we saw in drawing to scale is not my forte, so 0.034. So if I want my one-sided p-value, I'm going to go away from this mean. So what I observed, 0.034 and less. So I want that left tail area here. So that will be my one tail. In order to get my two tail, I'm going to just multiply this one tail by 2. So the probability that z is less than negative 0.24. So I'm going to break it up into negative 0.2 and 0.04. So this tells me which row to go to, 0.02. This tells me the column, 0.04. So I get 0.405052. So then real quick to summarize here, my one-sided p-value is equal to 0.4052. Right off the bat, I can tell you this is a big p-value, right? It's really big. But then we need to focus on, do we even want a one-sided? Now, this was a two-sided test. That means I actually have to multiply this one-sided p-value by 2. And that's going to be really big. So multiply everything by 2. So now I have a two-sided p-value. And it's going to be equal to 0.8104. I think. Now I'm doing mental math, so definitely double check. So my two-sided p-value of 0.8, it's huge. It's definitely bigger than 0.10. This is not strong evidence. We did not find strong evidence that robots are making chocolate or assembling chocolate boxes at a different rate than the humans are. Definitely did not find evidence of that. So, looking at this first part here, I like to fill out what I know right away. So 0.05 significance level, my p-value, and you can write the two-sided p-value, or so 0.8104, just 0.81, that's pretty big. So we're going to fail to reject. We did not find good evidence that the robots are doing a different rate than humans here. Okay, and then for our second part, a p-value of 0.81, that is really weak evidence, like it's really weak. So I would say little to no evidence here. So little to no. I've seen some folks that'll write no evidence. I like to avoid that because saying no evidence implies that there's zero evidence. That's not actually true. It's just that the evidence we have, it's very, very weak. So we have little to no evidence to suggest that the proportion, and then we're going to immediately say, oh, the proportion of what? So what population? So all chocolate boxes assembled by the robot that what? So that are defective. And then here is where the alternative hypothesis comes into play. We wanted to see if they were different. So is that proportion different? Is different from 0.036. And in parentheses, I'm just going to say human rate. It's the human rate of boxes that are defective there. So little to no evidence to suggest that the proportion of all boxes that are defective produced by the robot is different than... Okay, one more example here. So we're looking at marijuana legalization and decriminalization in the U.S. So a lot of places have legalized it, and hopefully more places are decriminalizing it. So Oregon is one of those states that has legalized recreational marijuana. And we're looking at a research that they really want to know more about opinions here. So they want to make a confidence interval to find support for legalization of marijuana. And they want the margin of error no larger than 0.02. So my margin of error, 0.02. So that means when I put everything together and I get a confidence interval, it's not going to be any wider than 0.04. Like total. So, and I want a 90% confidence interval. So that tells me my z-star, 1.645. And I want to know what's this minimum sample size that I need to get in order to get a confidence interval that is this confidence level and no wider than that amount. So the thing I need to work out here is p star. So just looking at here, I don't have any prior sample information. I don't have anything to pull from. So I am going to use 0.5. because that's just the most conservative guess I could use. So plugging in here, I'm going to do this part first. So I'm going to have 1.645 for 0.02, square that, times 0.5, times 1 minus that is 0.5 again. Plugging that in, I get something like 1,691.266. So my sample size needs to be greater than or equal to 1,691.266. So if you think about it, you can't take a sample size of exactly that number, right? People are going to get really upset if you try to take 0.266 people, right? So you need to sample and always round up at least 1,692, right? Because if you round down, that's not quite enough. So you have to round up people, because we are surveying people here. So my observations are people take at least 1,692 people. And so that should finish up. Like, this was a couple of extra examples there. There are some your turn, and if you check out on the lecture notes page, there are some extra practice problems as well as solutions. So definitely check that out. Let me know as you have questions, and I look forward to hopefully discussing this with y'all by discussion board or email.